Hello, my name is Tiago Oliveira and I'm presenting Certified Compilation for Cryptography, Extended x86 Instructions, and Constant-Time Verification. I will start by presenting the two main motivations for this work. The first is that there was no support for instruction set extensions in available certified C compilers. Additionally, no constant-time formal verification tools were available that supported those same instruction extensions. This led us to realizing our approach using CompCert, a formally verified compiler, and our main contributions are adding support for instruction extensions and integrate a new constant time checker that performs verification at a pre-assembly level. Finally, we evaluate our tool by using SuperCop, a toolkit for measuring cryptographic software. This presentation will proceed as follows. First, some detail about the considered instruction extensions, followed by a description of the steps that were taken to extend CompCert with new instruction extensions, an overview of Intrinsics aware constant time checker, our experimental results, and to conclude, the upcoming developments. In 1999, Intel introduced the streaming SIMD extensions. This extension includes 8 new 128-bit registers and several instructions to perform operations over multiple data at once. As an intuition, these registers and instructions can be used to perform the same operation over 4 32-bit values. The subsize can vary between 8 or 64, depending on the extension version. The original SSE extension was specifically oriented to floating point operations, and in later versions of SSE, integer operations were also included. More recently, in 2011, Intel introduced AES-NI, or Advanced Encryption Standard, new instructions. This extension provides a set of instructions that allow to perform AES computations in hardware. The usage of AES-NI is motivated by major performance improvements when compared to software implementations, and also improved security. Instruction extensions are made available in C programming language through a mechanism called Intrinsics, also referred to as built-ins in some cases. Intrinsics are specially handled functions by the compiler that eventually get translated into the corresponding assembly instruction. Note that in some compilers, such as the GCC or CLang compiler, this may not be the case. In the optimization stage of such compilers, the expected instruction can sometimes be replaced or slightly rearranged if the compiler finds that that change yields better performance. At the bottom of this slide, we can find the list of intrinsics functions that are made available by AES-NI. Now, moving on to the next part, having x86 instruction extensions to CompCert. In this slide, we illustrate the CompCert architecture. The front end of the compiler, which corresponds to the first 4 stages, that is, the set of stages that take as input a program written in C and transform it into C minor. And C minor is a stripped down variant of C, and it's the input of CompCert's backend, which includes the remaining compilation stages, such as the register allocation, or at the later stages, the printing. In this work, most of the changes were performed at the parser and the register allocation. Now, I will present the steps that were taken to extend CompCert. The first step was the creation of a generic configuration file to model built-in functions. Each entry in this file consists in the descriptor of the built-in, and in this descriptor we store all the relevant information about it: its name, its return type, and also the arguments types, the class of the instruction, in the presented case the AES class, the number of immediate arguments, and the assembly instruction itself for the printing stage, and the boolean value indicating if this is a to-address instruction. This generic configuration file was automatically generated from the GCC documentation. The presented example corresponds to the AES key generation intrinsic. And to conclude, we took advantage of the already existing CompCert built-in mechanisms to inject these new definitions into CompCert. The second step that was taken was to extend CompCert's front-end, more precisely the parser. This was done in order to ensure that the previously defined built-ins were properly recognized and translated into CompCert's abstract syntax tree. Some changes needed to be made to the parser, for instance, to recognize intrinsic related attributes, such as the vector size attribute. We also introduced a new 128-bit scalar type, and these subsequent stages were changed in order to accept this new type. These changes, although they were small. And the third step was to extend CompCert backend. More precisely, the register allocation was extended to support the new set of 8 128-bit XMM registers. We added a new register bank to the machine description, while taking into account that these new registers, overlap with the registers that are already in use for the floating point operations. For this reason, the register allocation notion of interference needed to be extended. And lastly, regarding the CompCert semantics preservation, we needed to extend the semantics preservation theorem, which stayed equivalent to the original one. I will now introduce the intrinsics-aware constant-time checker. And for this, first I will talk a bit about the constant-time property. The main goal of the verification of the constant-time property, which is a countermeasure against timing attacks, is to ensure that the execution time is independent of any secret data. For a program to be constant time in relation to its secret inputs, its control flow or memory accesses must not have any dependency on secret data. Additionally, some other CPU instructions unrelated to the control flow or memory operations may exhibit some execution times variations depending on their inputs. For this work, we do not consider such instructions, but we think that this type of constraints could be integrated in our policy checker. With this checker, we address two limitations in the context of constant-time verification. The first is that there are no formal constant-time verification tools that support instruction extensions. The second is that the verification at source level doesn't guarantee constant time at the target level, unless the compiler is formally verified to preserve the constant time property. So, we designed the constant time checker that performs the verification at a pre-assembly level and operates in three steps. The first is the value analysis, where an approximation of the pointer's values is calculated. Then the type system, which infers values that may depend on sensitive data, and the policy checker, which ensures that the control flow and memory accesses don't depend on secret data. An overview of each of these steps is given next. In the value analysis step, we build a flow and context-sensitive approximation of the pointer's targets. And for this, we consider an analysis that can cope with bit vector arithmetic in order to infer more precisely the pointer's offsets. And the type system works in the following way. It starts by assigning a security level at each program point and each calling context, which is basically a stack of calling sites to each location. And the location can be a register or a memory position. A security level can be high if the location may contain or depend on secret data, and otherwise it is considered to be low. To support intrinsics in our constant time checker, we modeled an oracle that classifies built-in calls as being pure if they only operate on registers, and memory load and memory store if they perform a load or a memory store operation. This oracle was built on the generic configuration files that were previously mentioned in step 1. This ensures that our analysis is independent of the target architecture. And to conclude the presentation of this section, I would like to present an example based on AEZ, an authenticated encryption scheme. For this analysis, we considered an implementation of AEZ shipped in the SuperCop toolkit, and that uses Intrinsics. And by using our new checker, we found a constant time violation, a benevolent one, due to an immediate return if the padding was incorrect. We modified the code to store the exit code and only return it at the end of the function, and with this change the code was accepted and considered constant time by our tool. And now we move into the experimental results section. For the evaluation, we did use SuperCop, a toolkit for measuring cryptographic software that ships with more than 2,000 implementations. These implementations are organized in a three hierarchical level. At the top level, we can find operations, which consist in abstract interfaces for a given cryptographic component. Examples of operations are cryptohash or cryptostream for hash functions or stream ciphers, respectively. At the second level, we can find primitives, which are instantiations of operations. For instance, SHA-20 is a primitive. And at the bottom level, we find the actual implementations. Each primitive may contain several different implementations, targeting different architectures or having different levels of optimizations. It is common to find reference implementations, usually written in C or with the major goal of being portable, and some others, non-portable implementations, that may use intrinsics or are even written directly in assembly. So we configured SuperCop with different sets of compilers across different runs. First, and to establish a baseline, we configured SuperCop with GCC compiler version 5.4 and also CLang compiler version 3.8, both in 32 and 64-bit modes. And next, to evaluate the coverage and performance improvements of our extension in comparison with the baseline and other CompCert versions, we did an individual run for CompCert 2.2, which is the basis of our work, and another for the extended version. Finally, we also considered CompCert 3.0, both in 32 and 64 bits mode. After running SuperCop with these configurations, the results between these different runs were compared. The following table presents the total number of implementations that were compiled in each configuration for each operation. For compactness, in this table we only show operations with more than 10 implementations compiled for the 32-bit baseline. The full table is presented in our paper. But we can see significant increases in coverage across several operations, more precisely the AEEAD, or authenticated encryption with associated data, hash and stream operations. As for the global coverage value, we were able to compile 84 additional implementations due to the support of Intrinsics in our tool, when comparing with the CompCert version that served as basis for our work, namely the version 2.2. We also include the coverage results for AMD 64 architecture to get a sense of what would be the coverage penalty of downgrading from AMD 64 to x86. And with our extension, we are still on the top when comparing to the CompCert 3.0 configured for producing 64-bit code, and performance results will be presented next. The following table presents the performance ratios between the baseline, which consists in the fastest implementations that were chosen when SuperCop was run with GCC and C-line compilers, and the shown CompCert version. For the sake of this analysis, we only considered primitives that were able to have at least one implementation compiled with all the presented compilers. We also excluded implementations that contained assembly files for this analysis. We can see that the average cost of using certified compilation in cryptography can be huge. For instance, the average performance penalty for the considered primitives and for CompCert 2.2 is 21. This means that by using the standard CompCert 2.2 and in average, the code for the considered primitives performs 21 times slower when comparing to non-certified compilers. This is mostly due to the lack of support of Intrinsics, as it can be observed in the last column of the table, where we were able to lower the performance penalty down to roughly 4.8, or from another point of view, we perform 3 to 4 times better when comparing to the certified alternatives. And from our experimental evaluation, we can conclude that intrinsics are in fact a missing feature for the cryptography domain, given that we were able to simultaneously increase the coverage and lower the performance penalty with the proposed extension. We now proceed for the last slide of this presentation, the upcoming developments. We now plan to initiate a systematic study of the coverage of formal methods tools for cryptography implementations. The developed tool is available in the shown GitHub repository, and we are also planning in extending CompCert 3.7, or extend our work to CompCert 3.7, which supports AMD x64 as a target architecture. And also, of course, we would like to have AVX2 support in this future work. And also, there are some other ideas, just like exploiting intrinsic semantics to allow for better optimizations, and planning on updating our benchmark setup with more recent versions of the Supercop toolkit and the corresponding baseline compilers. Thank you for watching. Stay safe.